Good morning. Happy New Year. I'm going to go ahead and give you the notes for this upcoming section. Hoping to do this in person, but I think this will work out just fine. So feel free to speed me up if you need to and pause the video, whatever you need to do. I think you should grab your notebook and take notes with me. And I think you should practice all these examples that I'm going over. And let's jump in this new year and let's go ahead and apply some of those New Year resolutions that I bet you made. I know I made several myself. All right, polynomial functions of higher degree. We did start this before Christmas. So I am going to start with example 3 in your book. And you can see the directions in your book. It says use the leading coefficient test to determine or to describe the right hand and left hand behavior of the graph of each polynomial function. Use the leading coefficient test to describe the right hand and left hand behavior. Okay, so we hadn't quite done this yet, but we had used the leading coefficient test to get a good sketch. So a part is f of x equals x to the fourth minus 5x to the second plus 4. So I challenge you to go ahead and pause the video and look back in your notes and write down what you think the leading coefficient test is going to tell us. You'll see degree, and you'll see, can't remember what we called it. Well, we stated whether it was positive or negative. So you'll see that there. So assuming you went ahead and paused the video, so we would notice that this degree is a fourth degree because that's the highest value of the exponent, which means it's even. And then the leading coefficient test tells us that it is positive. Leading coefficient test, leading coefficient is 1, which is positive. So evens are like parabolas. They both work, the ends work together. They're both going up or they're both going down. And since it's positive, they're both going up. And they're praising. Okay, so just not even going to plug this into my calculator. I don't know exactly where this is on the graph, and I don't know if it is just exactly like a parabola or if it's sort of a W-shaped, but I know it's something like this. So I'm going to go with this W-shaped because I actually am looking in the book and I see that it is W-shaped, not quite like this W, but we're going to talk about the right hand and the left hand behavior. So imagine putting your hands on this graph at the ends. So what are these ends doing? Well, your right hand is going up. So the right hand is rising. And the left hand is also going up. So the left is rising. There's another way we can talk about this. Go ahead and put it back over here. So this, it can also be seen like on the SAT test. This would be negative infinity on the x, and this would be going toward positive infinity on the x. And for the y, this would be going toward positive infinity. This would be going toward negative infinity. So you might see as x approaches negative infinity, y approaches what? So that means as you're going on your graph and your x is getting closer and closer to negative infinity. Sorry about that. Okay, sorry about that. So if you saw this other way to write it, as x approaches negative infinity, what's y doing right here? So right here, x is going to negative infinity. They're just saying, what's this side doing? Well, y is going to positive infinity because it's pointing up. And then over here, for the right-hand behavior, as x is approaching positive infinity, what's y doing? Well, on this piece that we'd be looking at for the right hand, y is pointing up again. So y is going to positive infinity also. Alrighty. Next example. Okay, so for a polynomial function of degree n, I should have inserted for a polynomial function f of x of degree n, f of x has at most n real zeros. And zeros are found by setting f of x equal to 0 and solving it. So you can find the zeros just by setting the function equal to 0 and solving it. And so here's one truth about this function. And f of x has at most n minus 1 relative extrema. So for example, well, don't want to do an example quite yet. I want to show you this box here. So this is really important. The real zeros. If f is a polynomial function and a is a real number, then the following statements are equivalent. X equals a is a 0 of the function. X equals a is also called a solution of the function. X minus a is a factor, and a comma 0 is an x-intercept. So all these words are kind of interchangeable. And we're going to do an example that's going to help all these things to make sense. So example 4. Find all the real zeros of f of x equals x to the third minus x squared minus 2x. So we just saw on that other slide how we would find the zeros by setting f of x equal to 0 and solving. So if f of x is 0, we're left to solve this, and we always solve by factoring. And we were practicing with factoring before Christmas break. So the first thing you do is you would look to see if there was a GCF. And if there is, you want to factor it out. So if you'd like to go ahead and pause the video and try to factor this on your own, that'd be a great idea. So we're going to factor out an x because every term has an x in it. So factoring it out means that all these terms go down by 1x. So this is what we have now. And this factor right here is a quadratic, so we're going to try to factor that into two binomials. This x comes straight down, and then I set up my two binomials with my parentheses. Remember, we factor the x squared by x and x. We factor the 2 with 1 and 2. And this sign means that I'm going to have different signs. But this sign means my answer is going to be a -1. So when I subtract, I'm going to keep the sign of the biggest, which would be negative. So actually, I have these signs wrong. I want the 2 to be the biggest and be my negative. And you can always check your outer and your inner to be sure that they agree with this bx term here. Okay? So now that we've factored this, we have 3 factors. Let's back up to what that box said. It said x equals a would be a 0. It says right here, x minus a is a factor. Factors are just things multiplied together. So we have one thing times another thing times another thing. So we have 3 factors. And what degree was this? It was an x to the third. So you're going to set each of these factors equal to 0, all three of them. This one is already solved. This one you would subtract 1 from both sides to solve it. And this one you would add 2 to both sides to solve it. So the zeros are 0, -1, and 2. Now let's think about this box here. X equals A is a 0. X equals A is also a solution. So the solutions are also X equals 0, -1, and 2. It's not important that I wrote the X there this time, and I didn't write it up here. The factors are what we got when we finished solving, finished factoring. We have a factor of an X, we have an X plus 1 factor, we have an X minus 2 factor, and this last thing, step 4, says A, 0 is an x-intercept. That just means that all of these A's that we found, all these solutions that we found, are our x-intercepts. Kind of out of room here to write that, but these are our x-intercepts. So we learned a lot by doing this. We learned what each of our x-intercepts were. I have an x-intercept at 0, one at -1, and one at 2. That might really make these x-intercept points make more sense to you, seeing them on the graph and thinking, oh yeah, well that is -1, 0. That is 0, 0. And that is 2, 0. I'm going to erase those. Now let's look at that leading coefficient test. My degree is 3, which is odd, which means it's going to 1 up, 1 down. My leading coefficient is 1, which is positive, which means it's going to be this exact same shape that we had here. So the left hand is falling, and the right hand behavior is rising. Rises on the right, falls on the left. So we're falling on the left and we're rising on the right. In just a second, I'm going to talk to you about multiplicity. I think that is my next thing here. So for now, I'll just tell you that somehow I've got to create a continuous curve that's going to pass through each of these points. And so I'm going to start here on this leftmost part. I'm going through here. Somehow I've got to get down to this point now. I've got to go through it. And then I've got to go through this point again. So that's a good sketch of your function. This might go up quite a bit higher, and this might drop down quite a bit lower, but this is a great sketch. Also, let's back up to what we talked about right here. F of x has it most in real zeros. Well, how many real zeros did we come up for our f of x? Here, our n was 3. That's just the degree. And how many real zeros did we have? We had 3. And it said f of x has it most in -1 relative extrema. Those are the relative maxes and the relative mins. So for us, n is 3, so we would have at most 2 relative extrema. And we do. Right here is a relative max, and right here is a relative min. Alrighty, example 5. Actually, before we talk example 5, box here where we talk about repeated zeros. For a polynomial function, a factor of x minus a to the k yields a repeated 0. X equals a. of multiplicity k. So that's just saying if you end up with x minus 5, two of them, then you have a repeated 0 at x equals 5. And then what's nice about this, if k is odd, then the graph crosses the x-axis. If it's odd, it crosses the x-axis at x equals a. If it's even, then it touches the x-axis, and I sometimes will say bounces, because it does kind of look like if this was the x-axis here, it comes through and it touches it and it bounces right off. If it's even. If it's odd, then it's coming through, let's say this is our 0, comes through and it crosses through if it's odd. So if it's odd, it crosses. And if it's even, at our 0, then the graph comes through and it bounces right off. Bounces. And that's when we're even. And we will see one all the way through in just a second. Let's see, example 4. I'm sorry, this is example 5. Find all real zeros and relative extrema of f of x equals negative 2x to the 4th plus 2x squared. Okay, when we were talking about real zeros, we said the way you would find them would be to set f of x equal to 0 and to solve. And we would solve by factoring. Look back at that other example we did. And to factor, we first want to look for GCF. I have a greatest common factor over 2, and I have x squares that I could take away. This one has 4 x's, and this one has 2, so the greatest we could factor out would be 2. So you have the option of factoring out a positive 2x squared or a negative 2x squared. And personal preference for me, if my leading coefficient is positive, I always feel like it's easier to factor it if I factor that negative out. So, factoring's like dividing. So when you have the 2 and you divide it by the negative 2, you have a 1 left. There's 4 x's, we're factoring 2 out, so it leaves x squared. And over here, we have positive 2, we're dividing by a negative 2, that leaves a negative 1, which I probably won't write the 1. And I have x squared, and I'm taking both of them away, so actually I do need to use that 1 there. If your original problem has 2 terms, the piece that's left after you factored out the greatest common factor also needs to have 2 terms. So that 1 here is super important. Now you look at the factor that's left in the parentheses and you say, hey, you're going to factor again. And if you look back at the notes we took before Christmas break, if it had 2 terms, we would try to factor by difference of squares. And this is a difference of squares. So we're going to factor it into 2 binomials, taking the factor of the first term and the perfect square, or the square root of the last term. And difference of squares have different signs. So we have 1, 2, 3 factors. We're going to set these factors equal to 0 and solve them. You can do this in your head if you'd like. So here on this first one, we're going to divide by the negative 2. So 0 equals x squared, and then we square root both sides, and 0 equals x. Normally we'd say plus or minus 0, but plus or minus 0 doesn't exist. So this time, right here, we had an x squared that was 0. There were 2 x's here that gave us the same answer? This is a repeated 0 with a multiplicity of 2, which is even, so it touches the axis. Let me just scoot these over. For the other one, 0 equals x plus 1. Subtract 1 from both sides. 1x, and we got one solution. 0 equals x minus 1. You add 1 to both sides. There was 1x here, and we got one solution. But altogether, this was a 4th degree, so we could have at most 4 real zeros. Well, we have 1, 2, 3, but this one was repeated twice. So 1, 2, 3, 4. So that's great. We could have at most n minus 1 relative extrema. So at most 3 relative extrema, and at most 4 real zeros. So let's just go ahead and sketch our graph. These are just rough sketches. You are going to plot these intercepts. And go ahead and put points for your x-intercepts or your solutions, your roots. And then we'll use our leading coefficient test. The degree is 4, which is even. So it's going to behave like a parabola. The leading coefficient is -2, which is negative. So instead of it being a parabola pointing up, it's a parabola going down. So my left hand behavior goes down, and my right hand behavior is going down. Now, when I go from left to right and I try to fill in my graph, the first 0 I get to is -1. It had a multiplicity of 1. There was only one of them. So that's odd. So my graph is going to cross right through there. So it crosses right through. And then I'm ready to see if I can get to this 0 next. So I look at the 0. It was a repeated 0 with the multiplicity of 2. So when I'm trying to reach the 0, I'm going to come to that 0, but I'm going to not get to cross. I have to bounce right back off of it. But the graph does touch it, but then it bounces right back off. And then it's ready to finish by going through the 1. The 1 had a multiplicity of 1, which is odd, so it crosses through again. And you see now it's going to cross, cross through and keep going down with that right hand behavior that we sketched in already. Looks like we have a relative max here. Looks like we have a relative max here. Looks like we have a relative min here. That's 3 relative extrema. That's the most it could have. And I think that's it. Alrighty. Example 6. Find all the real zeros of f of x equals x to the 5th minus 3x to the 3rd minus x squared minus 4x minus 1. So if we want to find the real zeros, we're going to try to set it equal to 0, and we're going to try to solve by factoring. We do not know a way to factor 5 terms. There is no GCF other than a 1 here, so I can't factor that out. So I don't have a way to factor this. So in order to find the solution, I would need to look on my calculator. I would need to put this into y equals and see what the graph looks like. And right here in the book, you see the graph for it. And the real zeros are the places where the graph is going to cross the x-axis. So we're going to mark them. And they've gone ahead and calculated that for us. We could calculate it by doing second calc zeros, and then it would say get a little to the left. Let's say we wanted to look at this -3 side of the 0 first. So let's get a little to the left, and then it would say then get a little to the right, and then it would say make a guess, and then it would give you this nice approximation. Same thing for this 0 then. You would do second calc zeros again. You would go a little to the left of it, then you would go a little to the right of it, and then you try to get right on it and guess it. And that's how it would give you this one. And then same thing over here. You'd say second calc 0, little to the left, little to the right, and then guess. So you could try that one around if you'd like, and just to be sure that you're getting the right 0 values as the book was giving. Okay, example 7. Find a polynomial function with these zeros. Oh, so this is the opposite. Earlier, they were saying, well, this is your polynomial function. Find the zeros. Well, now they're saying these are the zeros. You find the polynomial function. So the first thing we would do is we would say, okay, one of the answers is that 0. One of the answers is this one. And this is the other answer. And then to go back from a solution to a factor, you would do one of two things. One would be that you could add this a half to both sides. So you would get x plus a half equal to 0. And then your factor would be x plus a half. Or you could just look at it and you could say, well, if x was equal to the negative a half, that must have meant it came from x plus a half. Here, the same way, you could minus the 3 on both sides to get that equal to 0. And then you would know that x minus 3 was your factor. Or if your answer is 3, then it must have come from x minus 3. And this one's exactly the same, so we have a repeated 0. So f of x is x plus a half times x minus 3 squared. Let me talk to you about that a little bit. Remember how if x plus a half equals 0 and you minus a half on both sides, you got the negative a half. During the magic method, when we got this solution of x plus a half, and we'd say, well, we don't really like it to be a fraction, so let's take that 2 and multiply it up here. So that's the other way to write this, as 2x plus 1 equal to 0. And if we solved that and divide both sides by 2, that also gives you x equals to negative a half. That's why we were allowed to do that sort of cheaty feeling little step during the magic method last year. So both this factor and this factor would both give us that 0 of x minus a half. But this factor without the fraction is easier to work with. So I would just, if you ended up with something like x plus 3/4, then I would go ahead and just do that, move that 4 up here, and call that 4x plus 3. It's just easier to work with than a fraction. And I'm going to go to the next slide. So now we're down to, let me rewrite that, 2x plus 1 times x minus 3 squared. I'm going to go ahead and leave the 2x plus 1 alone. I'm going to use our rule that we were practicing for squaring a binomial, where we squared the first. We multiplied this together and doubled it, and squared the last. Oops. So, square the first, x times x. Multiply x and 3 together, get negative 3x and double it, and square the negative 3. And then the last step is we have to multiply all this out. So it's a ton of distributing. So it's distribute, distribute, distribute. And then it's distribute, distribute, distribute. Then it's lastly, you're going to look for your common like terms. That's the only 2x to the third. We've got an x squares here. You got an x terms here. And one constant term. So this is the polynomial function that had those original zeros of x equals negative a half, x equals 3, and x equals 3. All right, I think that's a great spot to stop at. And when you come into class on Thursday, we will just be working through problems using all these things. Okay, I'll see you all then.